So yeah, hello from Adelaide. And sorry, I don't have a talk, a dance or a song. But I hope I have anyway also an interesting talk. So thanks for inviting me to give this talk about the Cherenkov Talos array, short CTA. So in the next 20 minutes, I will introduce to you this next generation observatory, and I will also talk about the KeySense project and highlight some synergies between CTA and Australian facilities. All right, so how does CTA work? So CTA will be an array of imaging atmospheric Cherenkov telescopes. When a gamma ray enters the atmosphere, it creates a particle shower, and the particles in the shower, they will travel faster than the speed of light in the medium atmosphere, and consequently they emit Cherenkov radiation. And this light pool of Cherenkov radiation is roughly 50,000 square meters on the ground. And if we place our telescope there, we can measure this light. And you can see here an example of how our cameras would see a gamma ray event. So CTA will have different sizes of telescopes, large, medium, and small size telescopes. The large size telescope will be responsible for the low energy range, starting from around 20 GeV, and the small size telescopes are responsible for the highest energy range, going up to roughly 300 GeV. Large size means a mirror of 23 meters, medium a mirror of around 11, and small a mirror size of 4 meter diameter. All cameras are equipped with thousands of pixels, and every pixel is either a PMT or a silicon PM. And depending on the telescope we're talking about here, they have different fields of view ranging between 5 and 10 degrees. All types of telescopes, there are already prototypes being built and tested. You can see here the LST prototype in La Palma, the MST prototype in Berlin, and the SST prototype in Sicily. With all the telescopes, we are already taking engineering data, which are leading to expected results. The SST prototype has detected the Crab Nebula, which you can see here, and the LST detected the Crab Pulsar, showing here. These telescopes will be placed on 2 sites, one in the south and one in the north. CTA South will be placed at the European Southern Observatory in Chile, and it will host 14 of the medium-sized telescopes and 37 of the small-sized telescopes in its first construction phase. Later on, there will be more. CTA North will be on La Palma, next to GO2, which some of you might know, and it will host 4 large-sized telescopes and 9 medium-sized telescopes. So these 2 sites will constitute the CTA Observatory, which will be the first open, proposal-driven observatory for ground-based gamma-ray astronomy. CTA's data will be fed into a virtual observatory, and this observatory will also provide tools for visualization and analysis. And it is planned that at least the highest level products will also be mirrored here to Australia to a virtual observatory so that all of us can make use of this data. The CTA Observatory is governed by a council which is composed of shareholders from 11 countries and the ESO. A few highlights I would like to mention. Just 2 weeks ago, the board of the governmental representatives approved CTA's cost book and the scientific and technical description. And this is fundamental to establish the final legal entity of CTAO as an ERIC, which is the European Research Infrastructure Consortium. And this ERIC is expected for next year. And once this ERIC is established, we can officially start with the construction afterwards. Another thing I would like to mention is that the CTA signed a memorandum of understanding with SKA to facilitate sharing knowledge and expertise. So here's an overview of how the observatory is designed. And you can see that the telescopes will take data of roughly 1,000 petabytes per year. They will be processed on site, and roughly 3 petabytes per year will then be stored on site and then transferred off site. It will be processed there, and then in the end, it might be something like 10 to 100 terabytes per year that will be stored in the science archive. And this science archive is then available to the users, to scientists, basically to you. And it's also connected to other observatories. We will receive alerts from other telescopes, but we will also send alerts to other telescopes. All right. The CTA Observatory will work in very close collaboration with the CTA Consortium, which is involved in was involved in the array design. It is involved in supplying components, often as in-kind contributions, and it also developed and detailed the key science goals of the observatory. The CTA Consortium consists of, or is made out of over 1,500 members from 25 countries and 150 institutes. CTA Australia is involved with 7 universities and is being led by the University of Adelaide. CTA Australia is providing funds from the ARC, which are funds from 3 LEAF projects, which are mainly used for the constructions. We also have funds from NCRIS and AAL, which are used for the membership fees, but also for our science engagement. And for example, we used it for organizing multi-wavelength linkages meetings, where we bring together scientists from CTA and from the different Australian facilities. And those meetings were always really fruitful and really good. So what will CTA achieve? What can CTA provide? So here you can see our main performance plots. On the left side, you can see the expected sensitivity. On the right, the angular resolution of CTA cells. And you can see, compared to current instruments like MAGIC and HASS over here, CTA will be much more sensitive by a large factor compared to these. And similar to for the angular resolution, CTA will provide much higher angular resolution. CTA defines 3 major themes, which are understanding the origin and role of relativistic cosmic particles, probing extreme environments, and physics frontiers. And these themes are outlined in our publication, Science with CTA, where we also outline our key science projects. And these key science projects basically consist of several sky surveys, some deep targeted observations, follow-up of transients, and monitoring of variabilities. And I would like to note here that our membership actually already enables Australian involvement in many of these key science projects, such as the Large Magellanic Cloud or the Galactic Plane Survey. But before I go a bit more into the key science projects, I will quickly like to talk about CTA's multi-wavelength needs. So CTA will need, basically all key science projects will need a lot of multi-wavelength data. And for example, the cells will need more than 1,500 hours of radio observations and more than 3,000 hours of optical observations. And yeah, it's obvious Australia will be essential to cover these needs. So as you've seen on the previous plot, we need roughly 1,500 hours of polarimetry in the south. And we support this by one of our LEAF funds, where we develop a new polarimeter for faint targets. In another LEAF application we are involved in, this application is trying to make the 2.3 meter exciting spring observatory robotic, and that would provide us with observation time for CTA and for our polarimeter. So why is optical polarimetry interesting? So here's an example of a multi-wavelength campaign of an AGM BLUC S50716. And what you can see here in the bottom, you can see there's a sudden swing of the polarization angle. And this actually is at the same time of a TeV flare here in gamma rays. So AGMs are topic of a key science project, which will actually involve quite a variety of science, or will study a variety of science via different programs. So one of these programs is the long-term monitoring program. And in this program, we want to cover all known types of AGNs. And to have a representative samples of them, we want to cover them with 2 to 3 targets per class. And here on the right in the table, you can see a list of potential targets that we want to observe. It is planned that we observe these targets for roughly 30 minutes per week. And with that, we can study and probe variabilities, low and intermediate variabilities. So variability on annual time scales is related to the duty cycle of our source, and also to binary black holes, the jet precession and accretion disk processes. Variability on timescales of days, weeks, or months can probe emission region in the AGN jet, such as its size, geometry, and location. And by understanding the emission region, we can then also gain more insight in the acceleration and emission mechanisms. Then there's another program for high quality spectra, which we want to cover with different classes of AGNs at different redshifts, ranging from 0 to 1 in redshift. And with these high quality spectra are very important to distinguish between leptonic and hadronic emission scenarios. So for example, here in this example, in blue, you can see the models of hadronic and a leptonic model, and in white, you can see current observations, and it's quite clear with, current observation, we can't really distinguish between them, and we would need a very high sampling of the spectrum, like from CTA, to be able to distinguish between these two models. With these high quality spectra at different redshifts, we can also study the evolution of blazars, such as the blazer sequence. And very interestingly, we can also measure the extragalactic background light. And CTA can actually provide an indirect precision measurement of the EBL density. Another target of high quality spectra will be 2 radio galaxies, Centaurus A and M87. And in 2019, I guess a lot of you will remember the Event Horizon Telescope took the first image of a black hole, and that was M87. So yeah, quite an exciting source that we want to target with CTA too. And why are radio galaxies interesting? So the thing is that radio galaxies are less biased by relativistic beaming, because their jet is not pointing towards us. So that also means that we can actually observe different regions, or we get a different view of the AGN, and therefore have different views on or different possibilities to learn about the AGM, and that might also help us to in the AGM unification and to figure out what differences there are. And by understanding the emission of a radio galaxy, we will also gain some insights of other types of AGMs. The next program is a FLARE program, where we follow up external alerts and from other telescopes, and internal alerts from ourselves from the long-term monitoring program, and also some alerts from so-called snapshot observations, which are observations that are very, very short of a list of roughly 80 targets. So here we can probe a rapid variability of timescales of hours or minutes, which can put very strong constraints on the Doppler factor, particle acceleration, and cooling processes. This program will also be very interesting for increasing the population of flat spectrum radio quasars. These sources are typically very variable, and therefore it's quite hard to detect them in a quiescent state. So we need to catch them during a flare. And during a flare, we might even be lucky to catch very high redshift sources. And looking at a list of the highest redshifts, high energy, these sources, the three highest ones are actually flat spectrum radio quasars. So I'm coming now to another KeySense project, which is a KeySense project about transients, which will target a variety of different transients, from gamma ray bursts to other transients. And you can see here on the right, CTA sensitivity dependent on the observation time. And you can see for comparing to Fermi in the GeV range, it's something like 10,000 times better. Compared to current TeV observatories, it is roughly a factor 10 better. And together with a field of view of between 30 and 70 square degrees, CTA will basically be a transient factory. So I would like to quickly talk about one class of transients, which is gamma ray bursts. And just in 2019, we were finally been able to detect GRBs in the TeV regime. And here on the right top, you can see the GRB from Hess, in the bottom, the one from MAGIC, which were both published in Nature. And these detections of 3 long gamma ray bursts and 1 short gamma ray burst at redshifts between 0.06 and 0.6 actually opened a door to a new era of gamma ray astronomy. But CTA will actually see these GRBs up to redshift 4. And here in the bottom, you can see a simulation of a light curve, which has a resolution of seconds, and spectra that we can produce will have a minute resolution. Another KeySense project is the Galactic Plane Survey, which will be something like 5 to 20 times more sensitive than existing surveys, and will provide a better angular resolution. Again, here the plot is a simulation of how we think it might look for CTA. So here now a different view of the galactic plane. The blue dot here, that's us, and the blue circles, that's how far current surveys have seen the galaxy so far. And CTA will actually see much further, and it will see the whole galaxy. Yeah, almost. So some sources that are in our galaxy are so-called pavitrons, which are gamma ray sources above 100 TeV, which are therefore related to, or thought to be related to, 1 PeV protons and electrons. And the experiment LASSO has just recently, just a month ago, revealed some of these gamma ray sources above 100 TeV, and you can see they're mapped down here. But still, it's not clear what the particle accelerators are. Are they supernova remnants or pulsar wind nebula, maybe stellar clusters? We don't know yet. So that's why we need high resolution observations from CTA, but also from other multi-wavelength measurements. For example, to be able to model the gamma rays from a pi zero decay or from bremsstrahlung, we need a measurement of the ISM, the interstellar medium gas. So, and these kind of surveys, it's quite obvious again, there are lots of synergies to Australian surveys such as GLEAM, GasGab, POSSUM, or EMUM. So let me come to my conclusion. CTA will be the first ground-based gamma ray observatory. It is funded with 320 million euro for the first construction phase, where we will build 4 LSTs, 23 MSTs, and 37 SSTs. Australia is a member country, which means every Australian can access CTA data, at least after the proprietary period of 1 year. CTA will perform sky surveys, deep observations, follow-ups, and monitoring, and there are a lot of key science projects which offer very interesting synergies to Australian facilities. And Australia will actually be really essential for CTA to cover its radio and optical needs. Yeah, so, okay, I'll finish here. Thank you.
Okay, thanks, Sabrina. So we've got a couple of minutes for questions. I'm just going to pass the chat to Sabrina, and just if you want to just read them rather than me reading them out to you.
Okay, so
two minutes. We've got about 5 questions. So take the first one.
Yeah.
And then pick and choose.
Okay, thank you. So there's a question from Adam Batten. What is the reasoning behind putting all the SSTs in the south and all the LSTs in the north? So first of all, yes, there will only be SSTs in the south, and the reason is that the south just has an amazing view of the galactic plane. And for the galactic plane survey, we are interested in the highest energies. So that's why we will put the SSTs in the south. Also in the south, we have much more space than on La Palma. So it's also a logistical reason, but the main reason is scientific, that we want to measure the galactic plane with the SSTs in the south. And then regarding the LSTs in the north, so the first construction phase will only have LSTs in the north, but in the next construction phase, there will also be LSTs in the south. We just started with the north because the prototype was built in La Palma. It's much easier to access because it's mainly built from Germany, Japan, and Spain. So it's just very accessible for building a prototype. And that's why we started with the north. Okay, another question from Jonah Hansen.
Sure. So the next person.
Oh, yes.
You started answering some of the questions in the thread.
Oh, you did?
So one more, then we need to move on. Just pick one and we'll move on.
I'll just pick the next one. I don't have time to read the others. So Jonah Hansen is asking, CTA cells was said to be at Paranal. I assume you would need a fair bit of space for these telescopes. Is there room on the mountain, or are they being put nearby? Well, I think the ESO space is quite large, and yes, we need a lot of space. Yeah, it is. Yeah, Gavin just said it's in the valley between the mountains.
Okay.
All right.
All right. We need to move on from there. Thanks again, Sabrina.
Thank you.
All right. Echo? No, we're good now. All right. So the next talk is about gravitational wave astronomy and the first observation of neutron star black hole binaries. Okay, we've got 25 minutes total, 20 minutes for the talk. I'll try to slip in with a 5-minute warning. So it looks like there's 2 speakers here. So yeah, take it away.
Thanks. Hi, everyone. So yeah, we're going to split this talk between myself and Rory. So it'll be an overview of gravitational wave astronomy and also about the first observations of neutron star black hole binaries. So first of all, thank you very much to the organisers for the invitation to give this talk. It's a real pleasure to present this science. Oops. Oh, got it. So to begin with, I'll do like an overview of the gravitational wave observatories around the world. So there's the 2 LIGO sites in the US, Virgo in Italy, Geo 600 in Germany, Kaga in Japan, and LIGO India, which is coming soon. So they are laser interferometers, and what we measure is the change in distance of the relative length of the 2 arms. So you can see the arms on this schematic here, and that corresponds to the amount of, like, the strain of the gravitational wave signal as it passes through the interferometer. So what kinds of, sorry, go the right way, what kind of signals are we looking for? So far, and I'm sure you've all heard about the black holes and neutron star binary systems that we've seen to emerge. These are all compact binary coalescences, and this falls into the category of modelled because we have a good idea of what the signal looks like, and short in duration. They're transient, quick signals. But you can also use these detectors to find a lot of different types of signals too. So there can be unmodelled signals, which are kind of burst signals, which maybe we don't have a good idea of kind of signal that we're looking for. And Meg talked a bit about that yesterday, of how you can try and find these kind of signals. And then they can be long too. So continuous gravitational waves are long lasting and also stochastic. So to begin with, I'll talk a bit about compact binary coalescences, and then shuffle over to a bit about the latest continuous wave gravitational wave searches. So to date, there's been 3 different observing runs. In the first 2 observing runs, there was the first binary black hole detection, the first binary neutron star detection, and by the end of that, we had 11 detections. And then the most recent observing run is observing run 3, and this was split into 2 halves, so A and B, and between them there was a month-long gap which was used to take the detectors out of observing mode for commissioning upgrades and sort of general maintenance to maintain that sensitivity and improve it. So in the first half of observing run 3, there were 39 detections from the LIGO and Virgo detectors, and then in the second half of observing run B, I don't know if someone was trying to say something there. I'll carry on. So the second half, observing run B, is currently being analysed as we speak. So we're working on this. The whole collaboration is working on analysing these signals, and we'll hear a bit about the 2 of the highlights of this of these results so far in the neutron star black hole binaries, which Rory will talk about in a moment. And I'll just also add that Kagra joined. Went into observing mode and did a short 2-week observing run with Geo 600 at the end of the 03B. So, and stay tuned, yeah, stay tuned for lots of exciting results from 03B. So I thought I'd give a quick overview of how we go from the interferometer data to the parameter estimation results and what kind of goes into producing this science. So what we get from the observatory is like a raw voltage signal from a photodiode, which is measuring the intensity of the laser light at the output port, which is due to the change in lengths of these 2 arms. And from that, we work out what kind of signals are producing the gravitational waves, and we can learn about the properties of the system and the population more generally. So to begin with, calibration of the data to get from the voltage to the gravitational wave strain, and also a lot of data quality checking goes into making this data as good as it possibly can be. So gravitational wave observatories are sort of very sensitive to environmental effects, so a huge task is to try and make them as sensitive as possible and understand any noise signals that are being appearing in the data. So this is quite a famous example here. You can see this is the binary neutron star observation GW 170817. You can see the track of the binary neutron star in the time frequency plot there, but over the top of it there is this humongous glitch, and this is an instrumental artifact, and a lot of work goes into trying to remove these glitches, and Meg talked a bit about how to model these glitches in her talk yesterday. So and I should also add that detection is sort of done in two different latencies. So during 03, there was public alerts, so the online detection was done in near real time, and alerts are sent out to astronomers around the world so that you can have a look and see if there's something interesting in the area of sky to do multi-messenger follow-up. And then the offline detection is done afterwards, and that benefits from all the calibration and data vetting that I've talked about. So moving on to parameter estimation. After that, we do the parameter estimation is basically a Bayesian analysis where we try and figure out as much information as we can about the signals that have been detected. So this is a more thorough analysis than the initial, like to get the parameters. And this is things like the masses, the spins of the component objects, the distances, what location on the sky it was. And the kind of results that you get out are this is GW 1905-21. And you can see where this plot is of the posterior distribution of the two component masses. So M1 is the larger, M2 is the smaller. So don't worry about this gray kind of area. This is in the definition that M1 must be bigger than M2. And so yes, so we try and get as much information as we can from these signals. And from that, we can do population studies and learn about what kind of formation channels these binary systems went through. And yes, Cherenkov gave a really nice talk of what has been done so far with the observations up to the end of 03A in her talk yesterday. And we can also think about tests of general relativity too. So no evidence has been seen so far for new physics beyond general relativity, but of course, as more and more detections come in, we'll continue to check for any deviations. So I thought I'd do a couple of little highlights from 03A so far. So this plot on the left-hand side is showing the results of the gravitational wave transient catalogue 2. So this is all of the results of compact binary mergers up until the end of observing run, of the first half of observing run 3. So you can see the mass ratio on the y-axis and the total mass on the x-axis. This is in solar masses. And each contour represents the posterior distribution of the of those parameters for each of the events that have been detected. So you can see that a few have been highlighted in this plot, which are particularly interesting examples of what has been seen, but it really is a population now. We're starting to see many different events of different types. So the one I've highlighted here is GW 1905-21. And this is the biggest binary black hole that has been observed to date. And it's sort of around 85-ish solar masses, merged with something around 60 to 70 solar masses, you can see on the plot here. And this is the one that has been spoken about a little bit earlier in the meeting and is possibly the result of a hierarchical merger. So the two black holes that formed this, this signal when they merged could themselves have been the result of mergers. And sorry, I keep going the wrong way. Another highlight from observing run 3A is this little one down the bottom here, just very small on that plot. And this is an interesting example because it's something that's around 25-ish solar masses merged with something which is much smaller than itself, so around 2.5 solar masses. And it's the most asymmetric system that we've seen so far. And if you want to have a look at the results yourself, you can head over to this website here and see the data release. It includes the bulk data release of the time series up to the end of 03A and posterior samples as well. And this is where we'll also put results from 03B when they are ready. So just to switch track a little bit in the last couple of minutes, continuous waves are another source of gravitational waves that we're looking for. And this is a very different kind of signal. They're persistent, quasi-monochromatic signals, and they should be in the data all the time. So what kind of thing is producing this signal? it's expected to be spinning neutron stars with some sort of deformation to them, some sort of asymmetry. So, so far, we've been observing run 3 for various different types of continuous wave signals. So you have, like in this instance, I guess it's worth specifying that neutron stars and black hole mergers, or neutron stars and neutron star mergers, produce gravitational waves. But in this case, we're looking for gravitational waves from the neutron star itself. It's spinning, it has some asymmetry to it, and as it spins, it produces gravitational waves. So a few different searches have been done already, and the results are out, so you can have a look at these papers here. And Australia has a huge kind of impact in continuous wave searches, because one of the pipelines that is used by the collaboration has built in Melbourne, and there's also a large group in ANU which are working on continuous waves, and also in Adelaide. So these results, I'll just highlight just the one, are from the young supernova remnant search. So these are kind of young neutron stars where we have kind of maybe a good reason to suspect they might have some asymmetry to them. No detection has been made so far, but even non-detections can contain information, of course. So this plot is showing what we can learn about the neutron star ellipticity. We can place upper limits on the neutron star ellipticity for supernova remnant targets based on non-detection of gravitational waves. So this is the 95% upper limit. A broadband frequency search was made using 3 different pipelines in this search, and the banding is the error due to the distance estimate for these targets. So, and also stay tuned, because there's going to be several other O3 analysis that are in preparation at the moment. So with that, I'll hand over to Rory, who's going to tell us all about black hole and neutron star results.
All right, thanks, Anna. You've got about 7 minutes left of your time, okay?
All right. Hi, everyone. So I'm Rory Smith. I'm based at Monash University. So it's a real pleasure to be able to talk to you about these latest new discoveries that were announced just a couple of weeks ago by the LIGO and Virgo collaboration, the first observations of gravitational waves from the mergers of neutron stars with black holes, not just 1, but 2 of these events, but also the first sort of really confident observation of neutron star black hole binaries. Sorry, how do I skip to the next slide? Thank you. I just want to begin briefly by showing this plot, which I'm sure you've seen sort of various versions of throughout the conference, the so-called graveyard plot. And I think this is a really beautiful way of summarizing our current observational knowledge of compact objects that are primarily formed through stellar collapse, so black holes and neutron stars. So up until the end of the first half of LIGO's third observing run 03A, we had observed gravitational waves from binary black holes and binary neutron stars. And now these 2 new events kind of complete the trilogy of compact binaries that can form from neutron stars and black holes. The first event, GW 200105 here in orange, was the first observation of the neutron star black hole binary coalescence, observed on January 5th, and then just 10 days later on January 15th, we observed the second event here in blue, GW 200115. And so sort of coming back to the global picture of compact binaries, this now, we sort of are in a position where we can survey the kind of continuum of compact binary coalescences, and this has very broad implications for stellar astrophysics and fundamental physics. So I'll just go over 3 kind of topics very quickly in the next kind of 5 minutes, I guess. I'll say something about the masses and spins of the binaries, what we know about the smaller objects, where we kind of think they're neutron stars, and how these systems formed, and some of the merger rates, the first kind of direct inferences on the merger rates. For those of you who are not in LIGO, this guy here is one of our dear leaders, Ray Weiss, who was one of the founders of collaboration. So on to the characteristics of the binaries. So our mass measurements are really encapsulated by this plot here. This is the 2D posterior distribution on the source frame component masses. So the heavier mass here, M1 on the x-axis and M2 on the y-axis. So the shading corresponds to posterior probability density for the two events. So in orange, the first event, and in blue, the second event. And these two plots here are just the 1D projections of the component masses. So just running through this table, which shows some summary statistics on the masses. So starting with the first row, this is the first event, GW 200105. And its primary mass here, this is the median posterior estimate of about 8.9 solar masses. And these uncertainties, we're quoting the upper and lower, the distance from the median at the upper and lower 90% credible intervals. So at about 8.9 solar masses, and within uncertainty, this really characterizes the primary as a black hole. And the secondary at 1.9 solar masses, and again, within the 90% credible region, uncertainty, sort of plausibly categorizes it as a neutron star. And I sort of stress the word plausibly because at the moment the masses by themselves don't directly sort of distinguish or characterize these systems as neutron star black hole binaries. And I'll say a little bit more about other information that we can use to do that. So moving on to the second event here in the second row. Again, there's a similar qualitative story. So the primary mass, the heavier object, sort of firmly categorized as a black hole at about 5.7 solar masses. There's a slight, well, modest support that this black hole may be in the so-called lower mass gap between 3 and 5 solar masses, where there's kind of a dearth of black holes. And again, it's secondary, it's sort of putative neutron star. It's about 1.5 solar masses. And again, within sort of uncertainty, this is very plausibly a neutron star. I'll say a little bit more in a couple of slides on sort of extra information that we might have to be able to categorize it as a neutron star. I'll just briefly talk about the spins because this is interesting formation scenarios. The two bits of spin information here that we're reporting are the dimensionless spin magnitudes on both objects, so just how rapidly they're spinning, and also the spin tilt, so how the spins are oriented with respect to the orbital angular momentum. This plot here on the left is another posterior probability distribution. There's kind of a lot to unpack here. So I'll just run through this kind of slowly. So looking at the left hemisphere, the shading again is posterior probability density, and the spin magnitude measurement corresponds to like how spread out radial it is. So like the more shading going outwards, the larger the spin magnitude, and its orientation tells you something about the spin tilt. So here, this contour is the 90% credible region, and this is telling us that the black hole spin is no greater than about 0.2-ish. And again, the fact that its orientation is kind of spread completely across the hemisphere is telling you that spin tilt is essentially totally unconstrained. For the neutron star, or for the secondary, both the spin magnitude and its orientation are unconstrained. So again, the primary spin here is about less than about 0.23 at 90% confidence. The story for 200115 is a little bit more interesting. Its primary spin magnitude is far less constrained. However, its orientation is much more constrained. So in this case, we largely rule out spin orientations that are aligned sort of with the orbital angular momentum. And at about 88% probability, we find that the Z component of the spin is actually less than 0. I should point out that this doesn't exclude the spin being 0 or even slightly positive and non-zero. However, we do largely rule out sort of orientations that are aligned with respect to the orbital angular momentum. Astrophysically, this is kind of weird and unusual. I should point out that we use very unphysical priors here, so this is kind of a slight caveat. Back to the nature of the secondaries themselves. So there are two kind of smoking guns that we may observe neutron stars. These would be if we had, as the neutron star inspirals around the black hole, the neutron star can deform tidally, and this imprints itself on the gravitational wave signal. We actually didn't measure any non-zero tidal deformability, which kind of would firmly categorize these as a neutron star, though this is not unexpected given the mass ratios of the binaries, but also the SNR, the signal to noise ratio of both signals is fairly low. Another possible sort of smoking gun would be had we observed any electromagnetic counterparts. This may occur if, say, the neutron star is tidally disrupted, if it sort of just shreds apart as it in spirals into the black hole, which is kind of shown in this cartoon here. Again, none was observed, which is expected given the sort of large distance to the source at about 300 megaparsecs in both cases, but also the masses and spins kind of disfavor tidal disruption anyway. So really this kind of story here is that based on the masses alone, we're kind of plausibly observing neutron star black hole binaries, but there's no real definitive observational evidence. I may have to skip some of these slides just in the interest of time. So one of the sort of additional things we do is to look at consistency checks on the secondaries masses. So in lieu of the fact that we don't have any definitive evidence that these are genuinely neutron stars. So this plot here is just showing kind of consistency of the observed secondaries with galactic neutron stars. The galactic neutron star masses here are shown in green, and these are kind of comfortably within the posterior distributions inferred from these two new events. We also check how consistent the secondaries masses are with the maximum allowed neutron star mass, which is a sort of function of the nuclear physics inside neutron stars. There are broad uncertainties, and we kind of consider a few models. I won't go through this in very much detail. Maybe if people have questions, they can ask afterwards. But basically, we find that the secondaries masses are less than the maximum allowed neutron star mass. The probability is about 95% in this case. So this doesn't exclude the possibility that, say, these are very light, maybe primordial black holes, though this is maybe slightly more of a speculative hypothesis. So I'll just move quickly on to the merger rates. We actually quote two different merger rates based on different assumptions about the neutron star black hole population. One, which is called the event-based rate here, assumes that the NSBH population looks either like GW 200105 or 115. And here we find the merger rates to be about between 12 and 120 mergers per gigaparsec cube per year, assuming a slightly broader mass range, which is informed by the actual search pipelines. We find that the merger rate can be between about 61 to 240-ish per gigaparsec cube per year. I don't particularly find these numbers that intuitive, so I kind of like to think about this in terms of how many mergers there might be throughout the universe. So for binary neutron stars, the kind of back of the envelope number is about one merger somewhere in the universe per 10 seconds, and the NSBH rate is about 10 times greater than that. So there's about one NSBH merger somewhere in the universe every couple of minutes. So based on these rates, we can look at different formation channels and kind of consider those which are consistent with the merger rates. On the left here are some formation channels that are consistent with the inferred rates. On the right, the ones that are excluded. So the ones that are still kind of plausible based on the inferred rates are isolated binary evolution, so two stars that evolve in tandem, go supernova and form black hole neutron star pairs. Formation in young star clusters encompasses isolated binary evolution, but it's also a more dynamic environment where binaries can swap components and so on. And also formation in active galactic nuclei, AGM, where things like migration traps and gas torques can drive the formation of asymmetric mass ratio binaries. Those formation scenarios that are excluded are those in globular clusters or hierarchical triples. The rates are just too inconsistent with those inferred from the two new events. So I guess in summary, I think the takeaway kind of message is, while there's no kind of definitive proof that the binaries in these new events are neutron stars, the results are nonetheless very suggestive based on the mass estimates. And in addition, we've sort of constrained the merge rate of NSBH binaries for the first time. So I think I'll stop there, and sorry for going over time. Thanks.
Okay, thanks Hannah and Rory for that. So looking at the questions in there, it looks like they've mostly all been answered through Slack already. So someone's been jumping in and answering all your questions already. So I think just in the interest of time, we'll just move on to the final talk of the session then. So let's thank Hannah and Rory again, and if you can unshare and we can let Roland pop up. So Roland, I've got you down for 15 minutes. Is that 10 plus 5, or what are we thinking here?
I think it's 12 plus 3, Gary.
12 plus 3. All right. So we'll work to it then. Okay. Do you need a warning?
Okay, thanks. Yes, thanks. That'll be good.
Yes.
G'day, well, I'm Roland Crocker from the ANU, and I apologise for standing between the audience and lunch. I'm going to be talking about something called the Galactic Center excess and the evidence that we've come up with that it's a phenomenon explained by millisecond pulsars, not unfortunately by dark matter. But this is work that was initiated in the master's thesis project of our former student Anuj Gautam, and it's currently in review. Anuj returned home to India earlier this year and spent a number of months in intensive care because of COVID, but I think he's doing better now. And Anuj was co-supervised by Lilia Ferrario and Ashley, and this work also involved the other people on the screen here. So what's the Galactic Center excess? It's probably the most exciting potential or plausible indirect dark matter signal that we have from astrophysical data. So it's an overabundance of gamma rays in the GeV band coming from the inner galaxy, basically from the galactic center and the inner galactic bulge. And it was, so this signal, you should keep in mind, is only accounting for about a few percent of the gamma rays that we detect from this very active region of the galaxy. So it was discovered very soon after the Fermi instrument was launched into space in 2009 by Dan Hooper and collaborators. And spectrally, in terms of the spectrum and its intensity distribution, its radial intensity distribution, and the absolute value of the intensity and the shape of the signal following something that looks like an NFW-like profile, this really does look like a WIMP self-annihilating, and it has led to more than 500 particle theory papers and its own Wikipedia page. So it's walking and quacking like a WIMP, but that's not a duck, that's a dusky moorhen. And so one should consider this is an extraordinary claim, and one should consider whether the evidence really is extraordinary. And unfortunately, the spectrum of the Galactic Center excess also resembles rather closely that we detect from individual gamma ray pulsars and individual gamma ray millisecond pulsars, and also what we detect from globular clusters. So the globular cluster gamma ray emission is thought to be dominated by millisecond pulsars. The morphology, when you actually look in detail, isn't a radially symmetric NFW-like profile, but it's actually tracing the distribution of the stars in the bulge, and that's not exactly radially symmetric. And then there's been a lot of work done on the topic of point source inference, looking at the statistics of sources which are actually too dim to show up as to be individually detectable, but which one can make statistical inferences about. And it seems like the good part of the signal comes from these very dim sources. So not a truly diffuse signal as one would expect from dark matter. Okay, so maybe it's not dark matter. Maybe it's, for instance, millisecond pulsars, but not so fast. So the people who want this signal to be dark matter, or maybe I shouldn't say they want it to be, but anyway, the counterclaim against the idea that this is an astrophysical signal connected to millisecond pulsars is that if we take the luminosity distribution of the local millisecond pulsars and use it to explain the Galactic Center excess signal, then we would detect a population of bright millisecond pulsars in the bulge, which we simply don't see. And another problem is that, again, if we look at, for instance, in globular clusters, there's a whole population of low mass X-ray binaries in those systems. And these low mass X-ray binaries, if we, again, normalize to the expectation from the globular clusters, we would predict too many low mass X-ray binaries in the bulge via this conventional recycling channel to MSPs that Matthew described on the first day of the conference. Okay, so our idea was to see whether we can evade these constraints rather naturally. So we tried a forward binary population synthesis model, predicting the population of millisecond pulsars that would be formed in the bulge over its history, and then looking at what the gamma ray emission from that population would be. And here we assume not the conventional recycling channel, that is where you have a neutron star produced in a core collapse supernova with a close binary companion from which it accretes and then is spun up to millisecond periods. but an alternative channel called accretion-induced collapse. And I'll explain that briefly in the next slide. But the point about accretion-induced collapse is that it's expected to produce low kicks for the neutron star, and that would be consistent with the close match that we see between the distribution of the stars in the bulge and the gamma ray signal. And we think, or we anticipated that it would produce far fewer low mass X-ray binaries. So this is something we needed to test. We adopted basically off-the-shelf parameter values for the binary population, that is in terms of the IMF and binarity fraction, initial separation of the binaries and eccentricities and things. And then with that forward model, we went on to predict the gamma ray and X-ray emission from that model population. Okay, so what is this accretion-induced collapse process? Very briefly, so this is a process which occurs in a small mass range for stars that are just slightly too low in mass to undergo a core collapse supernova, but end their lives as oxygen, neon, magnesium white dwarfs with close binary companions. And as the white dwarf accretes from the companion and is brought up close to the Chandrasekhar mass, there's a catastrophic loss of electron degeneracy pressure because of electron capture onto magnesium and neon in its core. And then this leads to a sudden collapse down into a neutron star. And you go from a compact object with a 10,000 kilometer radius to something with 10 kilometer radius, and conservation of angular momentum means that you immediately have an object, a compact object, which is spinning with millisecond periods. What's more, the flux conservation in this process gives you a magnetic field of 10 to the 9 Gauss or so, which is more or less consistent with observations of many millisecond pulsars.
5 minutes, Roland.
Sorry?
5 minutes.
Here is our predicted gamma ray spectrum and the galactic center excess data points. So we passed with flying colors basically the first test, which is that we reproduce the spectrum of the galactic center excess very, very well with this forward model. But as you might remember, that there were other tests that we had to pass. I should say here that there are two components to this emission. So you can see there's a bumpy component shown in the blue, and that is curvature radiation from the individual magnetospheres of the millisecond pulsars. And this broader yellow band is inverse Compton emission from cosmic ray electrons and positrons launched by the model millisecond pulsars into the interstellar medium close to the inner galaxy. So it passes a spectral test and the overall luminosity test. The other thing, another test that it passes actually is this question of the prediction of the number of bright, individually resolvable millisecond pulsars. So this is the DN-DS plot for the model population, showing is the blue band here. And you can see in the gray that this is the threshold flux at which Fermi will detect individual point sources. So basically, we don't predict any individually detectable millisecond pulsars from this population. So it's an old and dim and mostly spun down population of millisecond pulsars. The blue dashed line shows the limit at which a source provides a single photon to Fermi over its decade of observing the galactic center. And you can see that actually most millisecond pulsars in this model population won't even provide a single photon. So there's a gap here, which means that we don't detect a significant population of individually resolvable MSPs. And finally, we can predict the population of LMXB-like sources. So these are neutron stars which have been formed in the accretion-induced collapse process, but then reaccrete, or they re-establish accretion from the binary companion after the ARC event. And we predict at 14 gigayears cosmological time a population of about 100. And the green and red dots there are the actual X-ray constraints on the LMXB-like population of the galactic bulge. And you can see that we're also consistent with those observations. So that's the result. it seems like with the Ford model, it invokes the accretion-induced collapse formation channel for the millisecond pulsars, that this is a natural explanation for this galactic center excess signal. Thank you.
All right, very good, Roland. You actually saved me a couple of minutes there, thanks. All right, so we've got time for a couple of questions. So let's see, first one's actually from Rami, who asks, do we see a galactic center excess from the Andromeda galaxy?
Yeah, that's an excellent question. So it does seem like there is something like a, well, the first thing to say is that there is a gamma ray signal detected from Andromeda. The spectrum is somewhat similar to the galactic center excess. And the signal, so Andromeda, of course, there's some star formation. And for instance, you might remember the image that I showed of the sky in gamma rays early on. And you can see the whole plane of the sky is shining in gamma rays. So for the Milky Way, most gamma rays come from cosmic rays which are connected to star formation. Now, in Andromeda, the evidence, I mean, you're pushing the angular resolution of the instrument, but the evidence seems to be that the gamma rays don't correlate very well with either gas or with regions of active star formation. So there is some good reason to suppose that there might be some contribution of this sort of process of millisecond pulsars to that signal.
Okay, good. Let's see, I've got 3 more questions in the chat. So I'll just take the next one in there and I'll leave you to do the last 2 in your own time, perhaps. So Ilya asks, shouldn't we see more slow MSPs if AIC formation were common? That is there tension with observed pulsar velocity distributions?
Should we see more slow MSPs? Sorry?
If AIC formation were common.
Well, certainly the MSPs that we see we're not claiming that the AIC channel has to explain all of the local population of MSPs. And in fact, I think, for instance, Jared Hurley's work from about 10 years ago suggests that the AIC channel is supplying about half of the local population of MSPs. But for instance, so for this particular case here, for the galactic center excess, where we see the close match between the morphology of the gamma rays and the stars, we want a low kick progenitor channel, and the same thing can actually be said for the globular clusters. You don't, you know, with an escape velocity of only whatever 10 kilometers a second or something like that, it's hard to actually accumulate a sufficient population of MSPs with the conventional recycling channel and, you know, via core collapse to get the gamma ray emitting population of MSPs that's actually seen in millisecond pulsars. So yes, I'm not saying that all MSPs derive from the AIC channel, but in certain environments, you know, this is going to be an important channel. This is the claim that I'm making.
Okay, right, thank you. Okay, so let's thank Roland again and thank all the speakers of the session, and then we'll close the session. Thanks all.
Hi everyone, I just wanted to jump in and say that the IDEA Town Hall will be starting in approximately 15 minutes, and that will be on the Zoom channel number 3. So we won't start until 1:45, so 10:45 or 12:45. Thanks.